going to present mostly talk about metastability in stochastic system of spiking neurons. So a little overview of the talk. So first of all, I would like to give a few words about metastability. So I'm sure a lot of you already know at least a little bit about metastability, but I would like to speak a little bit about it to be sure that we are all at the same page. Then I will present the model I've been working on lately. And then I will present the result and maybe if I have some time, try to give the big ideas of the proof. Okay, so metastability. So metastability is a concept that came from physics. There is a lot of well-known phenomena in physics. Maybe the most well-known is radioactivity, but there are a lot of other phenomena like avalanche and supercooling water, for example. And so, informally speaking, metastability, when people talk about metastability, is something when you have some systems that tends to stay in some pseudo-equilibrium for some long time before falling into the actual real equilibrium. And it happens that people in neuroscience have been talking a lot about metastability lately, maybe in the last 10, 20 years. And so maybe I don't have time in this talk to enter into the detail of why this matter in neuroscience, but anyway, the purpose of my work was trying to, because in neuroscience I have the impression that it has been not very often been done in a rigorous framework. So this is the purpose of my work. And so it came the paradigm I'm going to talk about came from a paper from Cassandro, Graves, Olivieri, and Valles. And the name of the paper is Metastable Behavior in Stochastic System of Stochastic Dynamics, a Password Approach. And so the idea is that you have two properties. So the first one is the system stays out of equilibrium for unpredictably a long time, and before reaching this equilibrium, it's kind of stabilized in some sense, and so it is in a state that resembles stationarity, and I will try to explain what this means more formally. Okay, so the model. So we have a countable set of neurons that we write S, and for each neuron we have a presynaptic set of neurons, and for each neuron we have two point processes. So one for the spiking time, which is very common in model like that, and maybe which is less common, we have also a point process for the leak times. So it's different from most of the models that we have been seeing in this last talk, in the last few days, in which you have this continuous decrease of the membrane potential. Here the leaks happens at discrete time. And well, we do this mostly for mathematical reasons. So for each I, you also have, of course, the membrane potential. It's written xit, and you have a spiking weight function. So a little bit more formally, how does it work? The leak process, it's a potent process of stored gamma, and gamma is the parameter of the model. Sorry. And the point process n star, so the point process of the spiking point process, it is a point process with fluctuating rate. And what happens is that the rate at time t is given by phi, the rate function applied to the moment potential. And so you have a reset. When you have a spike, there is a reset. And as I said, when you have a leak, you also have a reset. And so the instantiation of the model I'm going to present today. So we're considering S, the set of neurons. It will be either the integers or so positive and negative integrals, either a finite window of this. And okay, so the first implication that we do is that we consider a nearest neighbor interaction. So this is surely a simplification, but maybe not the biggest one, because since the beginning of the work on this model that have been done, so I've been considering, and other people have been considering other graph of interaction. So for example, I've been working with my colleague Léo Planche on complete interaction, and I know that there is another NeuroMat fellow that has been working on the regulatory. So I'm sure that the kind of results I'm going to present today are not restricted to this kind of interaction. But well, because the talk is short, I choose the simplest one. And the other simplification is that to take the activation function, you take it like an arch result, like a step function. So this is surely a big simplification also. But well, when you're doing stochastic modeling of neuroscientific topics, you have to consider always the trade-off between the availability of mathematical tools and the biological realism. And one of the purposes of introducing this activation function is that it gives you access to a lot of mathematical tools. So because then, when you do this, the quantity of interest you're looking at for any neuron I at time t is whether the mean potential is strictly bigger than 0 or not. And by doing this, what you get is some kind of auxiliary process, which is a Markov process taking value in the state 0, 1 to the power s. And well, since the beginning work from Spicer in the 60s, there was a lot of work on this kind of Markov process, and you have a lot of tools to analyze this kind of thing. And so the idea is that you can use these tools to prove what you want to prove. And okay, so just a picture, because sometimes it's nice to have a picture in a mathematical talk. So how does this work, this intermathematical system? Simply, each neuron can be in two states, 1, 0. When it's in state 1, it spikes at rate 1. And when it spikes, it just resets to 0 and activates the neighbors. So they go to 1 if they were in 0. And you have a leakage parameter. You have a leakage phenomenon. And what happens is simply you reset to 0 if you are in state 1, and you do nothing to the neighbors. And this happens at rate gamma, which is, as I said, the parameter of the model. So one of the nice things is that you can do math with it, but you can also simulate easily. So I actually did it on my laptop, and what you get is this kind of thing when you take gamma small. And I'm going to explain in a minute what gamma small means. So as you can see here on the left side, at the top, you have an histogram of the time of extension, and in red you have the curve of the exponential function. And as you can see, it's pretty close to the exponential distribution. So this is, I guess, for 100 neurons. So this is the first of the two properties I've been talking about in the characterization of metastability I'm considering. And what you see at the bottom is a typical trajectory of the system. So what happens is that after a very short time, it kind of stabilizes and oscillate around some value for a pretty long time, and then it gets absorbed by the absorbing state of the system. And okay, so the purpose of introducing this model is to prove theorems, right? And this is the first theorem that was proven in a paper by Pablo Ferrari, Antonio Galvez, Eval Shaba, and Grigorescu. So this is a result of phase transition. So what they prove is that for the parameter gamma, you have a critical value. and that if you take gamma strictly bigger than the critical value, then the point process for each neuron I, the spiking point process stop with priority 1, and in other case, you have a positive probability that a neuron will spike infinitely many times. So this is when the state, like neuron state or the index of the neurons are z, so you have an infinity of neurons. So, well, you might say in actual biological neurons, you never have infinitely many neurons, but the thing is, using this kind of result, you can manage to prove other result in the finite setting. Okay, so this is the result that was proven with respect to the first part, the first property related to metastability. So you take the set of the neurons, you take instead of wall z, you take a finite window, and you define the last spiking time. And what you can prove is the following thing. So if you are in the subcritical region, so you take gamma less than the critical gamma, which is the same critical gamma as in the previous theorem, then you can prove that this thing, so the last time of extinction, so renormalized, it converges to some exponential random variable of low exponent of parameter 1. Okay, so this was a previous result, and now I would like to present some kind of new results that I've been working on, and it is related to the second part of metastability. So what does it mean that a system kind of stabilize, resemble to stationarity? So a way of formalizing this is simply the following. Yes. So what you do is you simply choose some neurons, so finite set F, and looking at each neuron, you just for some interval of time, you count the number of spikes, and you just average it with the length of the time interval. And then what you can prove is that if you choose correctly the length of the time interval, meaning it has to be big enough but not too big, you can prove that this kind of average always converges to some theoretical value. So what this means is that you never have big fluctuation before the extinction away from some basal value. Okay, so just, well, I wanted to talk a little bit about how you prove this kind of thing. So basically what you do, so we want to prove this, right? We want to prove convergence probability, so this is the thing we want to prove. And here, so you have this row here. And basically this is a quantity that came from the particle system I've been talking about. And this is the asymptotic density of neurons when t goes to infinity for the infinite particle system. And the main idea is you divide this probability into two parts. So basically you take the part, the difference between the point process system and the interacting particle system, and then you take the difference between the interacting particle system and this rho value. So you have this kind of thing. And then you take care of the two parts using different techniques. So for the first part, you use all the tools available you have in interacting particle systems. So it means duality and upper invariant measure and this kind of things. And you basically can, using classical techniques in this field, you can prove that this goes to 0. And then, well, you have to take care of this part here. And, well, you can do it using mostly considering conditional expectation and typical classical concentration inequality like Chebyshev or conditional version of Chebyshev. You manage to prove this kind of thing. Okay, now I wanted to talk a little bit about the equation, but maybe I will let that for the equation if you have any interest.
Thank you very much, Morgan, for this nice talk. Are there any questions in the audience?
Yes, I have one, if I can.
Yeah, Antonio, good morning.
Je peux faire, may I?
Yes.
Okay. Morgan, you made a comparison with the results of Antonio Marcos Barbosa. Could you please tell us more about this?
Oh, yeah. Okay, so it was with respect to the result of phase transition. So Antonio Marcos, I guess he considers the same system of integrating point process, but with the graph of interaction is a regular tree. So basically something like that, right? With constant degree. And he proves that there is a double phase transition. So he proves that with respect to the pattern of gamma, you have two critical parameters, you have two critical value, and for if in one of the phase, so it is the same, you have extinction. In the other phase, you also have this same kind of local survival, meaning that for each neuron eye, when you're looking at, you have the positive probability of having infinitely many spikes, but you also have another intermediary phase in which what you observe is that you have global survival. So for the system continues spiking infinitely many times. But if you look at each neuron, you tend to, yes, there is no activity with probability 1 after some long time. And so this is a little bit different from the previous setting, and well, it will be very interesting to try to investigate stability in this intermediate phase.
Thank you. There's another question by Guilherme.
Thank you very much for this very nice talk, Morgan. I just wonder if you have an idea of how the gamma C depends on the structure that you have defined. Is it possible to have an idea of how it behaves, or
on the one-dimensional lattice, you mean?
Yeah.
Well, well, I don't know. I can say that gamma C is less than 1, which is not a question.
No.
But no, I don't know how exactly depends on. So of course you can have, for example, you can have some relation of, if you consider lattice of higher dimension, probably you will know that the critical gamma will be bigger. But no, I don't have anything else.
Thanks.
Could you show us your last main result again, please?
This?
No. I mean, this one, the main theorem. So this is something like an ergodic theorem where you condition your system to survive, or something like this.
Yeah.
Okay.
So here I don't. You don't even have to
condition because you
condition because the probability of will go to 0 because of the choice of the length of the interval you've been chosen. But yeah, this is this kind of thing. Yeah.
Okay. And the expectation of Tn behaves like what as a function of n? Was the same question of Etienne yesterday.
Yeah. So so you know that it is so if you do, for example, n over the expectation of 2n, it will go to 0. So it is a little off. But other than that, I don't have an exact bond, but I'm pretty sure that it will be something like exponential minus n. Because of some other results that we know in other kind of systems that are alike.
Thank you. Can you go to the previous slide, please? Okay. See the result. I guess that Tn depends on T. No.
No.
No, it's a time of extinction.
Yeah.
Small n. Yes. No, I don't have any question.
Are there any other questions? On the YouTube channel, Christoph? No? Okay. So then let's thank Morgan again.